Insulated concrete formwork systems, abbreviated to ICF systems, in the design and construction of low-energy buildings. This CPD provides a company introduction to Jackon, covers the history of ICF buildings, describes EPS insulated concrete formwork systems, explains the construction process, and offers examples from previous projects. The learning aims of this CPD enable an enhanced understanding of the history and benefits of ICF buildings, ICF as low-energy building systems and the key features, EPS as ICF building materials and the characteristics, the key steps of ICF construction process and considerations. Let's begin with the company introduction. The Jackon Group is a family-owned corporation established in Fredrikstad, Norway in 1956. We are one of Europe's leading manufacturers of EPS, expandable polystyrene, and XPS, extruded polystyrene products. The company now has more than 800 employees in 8 countries, 21 factories and 7 sales locations. With the production of EPS and XPS insulation materials, intelligent building systems, protective packaging and EPS bead raw material, we have secured a strong position for the future in a highly competitive market. We have achieved a reputation for top-quality products, professionalism and service among our customers, and are known as a pace-setter within the industry. Our main technologies are extrusion, XPS, block and shape molding, EPS, and beads, which is the production of raw material. As a group company, we distribute our products mainly to European countries. Our product lines consist of Thermomur ICF, a modern method of construction molded from EPS, Atlas under-slab insulation, produced from XPS, Jacoboard construction boards and wet room systems, other structural insulation, both EPS and XPS, industrial insulation and packaging, PS bead production. Notably, we use higher density blocks, which surpass those that UK regulation advises. We are a market and customer-driven company, constantly striving to improve and develop new products, in close cooperation with our customers, as well as optimizing our service quality and customer satisfaction. There's over 30 years of continuous development and experience behind the Jackon Thermomur ICF framework product range. It's the leading brand and trialled and tested in the demanding Scandinavian environment. The high-density EPS is manufactured at our own premises using Jackon's own EPS bead under stringent quality control measures. It's a robust pre-formed block that interlocks to facilitate fast and easy assembly on site. Various block dimensions can meet different U-value requirements without the need for additional insulation. It offers high U values leading to excellent PSI values, and it works on a metric system. Vertical robust webs for secure fixing and secure blocks allow the free flowing of concrete. It's backed by complete European technical and environmental approvals, and Thermomur is approved by the BBA. House building in this country is often limited to a choice between on-site masonry construction and off-site factory-built timber frame construction. Construction with thermal insulated formwork is rather different. ICF is an insulated in-situ concrete system of building that is quick to construct and offers levels of performance significantly better than alternative methods of construction. The insulation formwork is made in a factory, which then gets erected on site. The concrete is then poured into the formwork wall blocks to establish strength. The building system was first developed in the 1950s in Germany and has been successfully used all over the world, from the hottest to the coldest climates. Over the last 5 to 6 years, around 5,000 houses have been built using such systems. It's also particularly popular in North America, where there are over a dozen substantial manufacturers, building a combined total of around 15,000 homes a year. The first ICF homes appeared in the UK in the 1970s, but their uptake was relatively slow, largely because there is such a strong tradition towards the masonry build sector within this country. ICF is now recognised as a standard form of construction by the Council of Mortgage Lenders for mortgage purposes, and is accepted by the major warranty providers, including BuildStore. The documentation and further information can be found on the ICFA Insulated Concrete Formwork Association website. Over the years, ICF has developed a reputation for being of interest mostly to customers who appreciate high quality and low running costs over and above reduced building costs, such as housing associations and care homes, where the owners have a vested interest in ensuring low long-term running costs as well as self-builds. The ICF Association states that ICF buildings can achieve lower space heating costs. ICF structures offer low U values from 0.30 watts per meter squared Kelvin down to 0.10 watts per meter squared Kelvin. The greater insulation and tighter construction helps conserve heating and cooling energy efficiently. Good acoustic performance. Due to the density and thickness of the concrete cores within the ICF, excellent acoustic insulation is provided. Fire resistance. The fire rating of the ICF wall system should be considered. Leading manufacturers of EPS incorporate flame-retardant substances in the manufacturing process for enhanced fire safety performance. Minimal damage. Concrete and construction-grade EPS are unaffected by water. If ICF buildings are in an area which is subject to possible floods, they will withstand the pressure of water and flood damage will be minimized. ICF properties exposed to water can be pumped and dried out, leaving the structure integrity unaffected. Since ICF systems are concrete frame structures, they can be designed to the relevant codes for earthquake zones and provide successful protection from heavy storms and high winds, including hurricanes and tornadoes. Rot and vermin. ICF structures do not rot and are unaffected by vermin and termites. Mortgage, insurance and planning acceptance. ICF structures as a concrete framed building are accepted by all reputable companies and organizations, providing they have passed the recognized third-party tests and standards that are needed to obtain building approval. Easily adapted for future needs. Because concrete frames offer a whole floor space without further load-bearing walls, it is easy to remodel and upgrade floor layouts in the future. The strength of the ICF walls allows extra floors to be added, subject to authority approval, and it is easy to add and tie in future extensions. The structural walls will also accommodate extra openings in the future if needed. Should even lower U values be required in the future, extra polystyrene could be fitted externally and reclad. Minimal maintenance required. Under normal circumstances, no maintenance would be required on the ICF walls in the life of the building. The internal and external facades could be subject to minor damage, which could be easily repaired or completely stripped and renewed. The building regulations make no specific reference to ICF as a construction method. However, the requirement with respect to several parts can be met by conventional concrete and masonry, and this data can, in many instances, be applied to ICF on a generic basis. Part A, Structure, provides guidance on meeting the requirements with certain forms of masonry construction for a given range of buildings. Since the basic structural element is concrete, in general, the same codes and standards will apply, and hence the building regulations may be met by following the recommendations given in the documents listed in Section 1 of Approved Document A3.1, which includes recognised British and European standards. Principal UK design codes for the design of structural elements, Eurocode 2, BS 8110 and BS 5628. The design of plain concrete structures is covered by Section 12 of Eurocode 2. BS 8500 is the British standard for specifying and producing concrete. Part 1 covers specification and gives guidance to the specifier. Part 2 covers the constituent materials in concrete and contains the information required by the concrete producer. Passive House is a rigorous voluntary standard for energy efficiency in a building. It results in ultra-low energy buildings that require little energy for space heating or cooling. The energy-efficient performance of ICF walls comes in large part from the insulative property of the polystyrene foam on the interior and exterior of ICF walls. Also, ICF walls can provide better air tightness and eliminate cold bridging. The most common type of ICF is made of expanded polystyrene. The related standards are BS EN 13163, Thermal Insulation Products for Buildings, Factory-Made Products of Expanded Polystyrene, EPS, BS EN 13499, Thermal Insulation Products for Buildings, External Insulation Composite Systems, ETICS, based on expanded polystyrene, BS 14933, Thermal Insulation and Lightweight Fill Products for Civil Engineering Applications, Factory-Made Products of Expanded Polystyrene, EPS, BS EN 13172, Thermal Insulation Products, Evaluation of Conformity, BS 6203, Guide to Fire Characteristics and Fire Performance of Expanded Polystyrene Materials, EPS and XPS, used in building applications. Expanded polystyrene insulation, EPS, is manufactured using beads of foam within a mould. Heat or steam is then applied directly to the beads, which causes them to expand and fuse together. Insulated concrete formwork building systems consist of an inner and outer skin of EPS, expanded polystyrene, tied together using either plastic, steel, or an integral web of polystyrene. The core is then poured with concrete, leaving the polystyrene in place to become the internal and external insulation of a structure. Fresh concrete is poured into forms built up to 3 meter high as a complete wall. This is normally done by a pump. Once the green concrete wall is set, it becomes a high-strength concrete frame structure with the formwork remaining in place as thermal insulation, providing U values ranging from 0.30 watts per meter squared Kelvin down to 0.11 watts per meter squared Kelvin. The lowest required U value by building regulations in England is currently 0.18 watts per meter squared Kelvin for walls in domestic new build, best starting point fabric only, and 0.22 watts per meter squared Kelvin for walls in non-domestic new build. The new Future Home Standard asks for U value of 0.15, which is also easily achievable with EPS insulated concrete formwork. The building system can satisfy the latest changes to Part L of building regulations, right up to Passive House standards. In addition to the thermal insulation values, ICF structures have very low air infiltration rates, almost all of which is accounted for by window and door openings. Consequently, there will be very little heat loss due to air changes, and this boosts the thermal insulation effect. Conversely, designers may need to consider the provision of other measures to ensure adequate ventilation. EPS has very low water absorbency. The core is specified as a highly workable concrete. This results in a low risk of voids. Due to the permanent presence of the insulation both during construction and under operating conditions, The concrete undergoes more controlled shrinkage and thermal strains, and, as a result, experiences very little shrinkage cracking. These factors combine to produce walls that are inherently resistant to rain and flood damage. The buildings don't get problems with damp penetration or mold growth. EPS ICF systems can provide the additional benefits which a standard concrete wall can provide. These include sound insulation. Most ICFs with 6-inch concrete core, 10 or 11-inch ICF wall, achieve sound transmission class ratings of 50 to 55 decibels, which means loud sounds faintly heard. The fact that ICFs can eliminate sound transmission at virtually no additional cost makes them very attractive for any project in which quietness is a selling point. Multifamily and hospitality projects, hotels, motels, multifamily and apartment construction are prime candidates. Schools, gyms and offices also appreciate the sound dampening. Durable structures with potential for long-life EPS ICF forms will not lose their insulative ability or rot or break down over time. Concrete does not require much maintenance and is not susceptible to rot, decay or attracting insects. Rapid construction. EPS blocks are lightweight, easy to assemble and require lesser skill levels and labour time as opposed to the traditional masonry construction method. The system allows the watertight building shell to be erected in days. The follow-on trades can therefore enter the building and start putting utilities and finishes into place much quicker than traditional building methods. Fire performance. The complete wall system has a REI fire rating. Typically, an EPS ICF system with a 150 mm concrete core has an REI 90 rating when clad internally with plasterboard and externally with a render system. To meet this standard, a concrete with a strength of at least C20 to 25 must be used. Building Regulation Document B calls for an REI 30 rating for most residential properties. Regardless of the final external finish, we recommend that all exposed surfaces of the EPS ICF systems are covered with a base coat of external render and a plasterboard internal finish. When designing multiple occupancy properties, the guidelines in Document B must be followed. Additional precautions, however, must be taken to ensure that fire doors are secured to the structural concrete and not just fixed to the EPS or any timber supports. Following the Hackett report, buildings over 18 metres should not be constructed with ICF systems. Sustainability facts about EPS. EPS products consist of 90% air and 2% polystyrene. EPS foams are sustainable building products, since after a few months of use, they save more energy, resource and emissions than was used for their production. EPS products are non-hazardous and do not require labelling as hazardous to health or to the environment. Most of EPS production scrap is recycled in the same production process. The durability of EPS is normally at least as long as the lifetime of the building in which it is used. EPS products can be reused thanks to their durability. EPS products can be mechanically recycled if clean and sorted, since polystyrene is a thermoplastic. Cleaning and maintenance is not relevant. At the end of life cycle, 100% incineration with energy recovery or 100% landfill. This is an example of EPS block systems with integrated fixing plates. The components interlock together to create a stable form, which contains the fluid concrete. The basic module consists of parallel sheets of EPS, joined by integrated fixing plates acting as ties, forming a hollow block which is filled with concrete. The parallel sheets of EPS provide 2 layers of continuous insulation that offer high compressive strength, are airtight and have no thermal bridging, and satisfies the latest changes to Part L of the building regulations. The stable walls bearing concrete are fire resistant and offer sound reduction benefits. The plastic braces provide stability during installation, offer reinforcement for the concrete core, and allow easy installation of rebars. The integrated fixing plate sit 13 mm beneath the surface and enable fixing of plasterboards, timber or brick slips. The system offers various options for possible exterior finishes, including timber, bricks, and it is also approved for render without any pre-treatment. Typical accessories of an EPS block system with integrated fixing plates feature 1. The alignment system. 2. A height adjuster. 3. Tapered angle strips. 4. Pre-shaped rebar links. And 5. Clips for vertical reinforcement. Typical technical data on formwork dimensions and thermal insulation values for examples of EPS block systems. They come in various dimensions, which offer different thermal insulation values and are suitable for different types of building. Example A is suitable for multi-story houses. Example B and C are suitable for multi-story passive houses. Example D and E are suitable for garages and commercial buildings. It is quite practical to design buildings up to 3 stories as concrete masonry structures without reinforcement. Any requirement for steel reinforcement will be dependent on the type, size and location of the building and will be recommended by the specifier, designer or structural engineer. The number of stories or height of the building is limited only by the structural design and local legislation. It is known that ICF systems have been used to construct buildings of 25 stories and is capable of reaching 40 stories. Stack heights with ICF construction can be particularly important when considering aspects such as footing elevations to grade, brick finishes relative to grade levels, and floor bearing heights relative to finished grade and each other. Lintels are light, pre-formed components delivered as part of the ICF system. Manufactured to suit the various opening sizes required for the building, they interlink with the other components. Reinforcing bars are laid inside, and the lintels are then filled with the concrete at the same time as the wall is poured, integrating the reinforced lintel with the overall wall construction. The thickness of the walls will vary according to the performance specification required. The thickness of the concrete core may vary depending upon the structural design, while the choice of the ICF thickness is subject to the thermal insulation specification. Typically, the total wall thickness may be between 300 mm and 600 mm. Radius walls are a unique architectural feature as well as having a practical value in building design. Small radius walls are typically less than 10 feet in diameter. The diameter of the radius is important because the tighter the radius, the greater amount of the material must be removed to create the radius. ICF forms can be cut to form radius walls of any degree, from approximately 2 to 100 feet diameter. Normally, DPC is specified for where the traditional DPC would be located. Alternatively, a non-solvent-based liquid DPC system may be applied onto the concrete at DPC level. ICF walls can be built with any foundation. The formwork is held in position by their self-weight, just as for traditional masonry construction. The normal procedure would be to build a couple of courses of the system around the perimeter, adjust it to the correct alignment level, and then fill with concrete to fix the position of the system on the foundations. Concrete must be placed into ICFs at a more controlled rate than on standard pours. Great care must be taken in selecting the proper materials, equipment and pour procedures. A simple designated C25 pump-grade concrete with a 150 mm slump and ideally 10 mm aggregate is typically specified. Ask for concrete supplied under QS-RMC or BSI quality assured schemes as a quality assurance. It's important to avoid improper detailing of wall penetrations, such as windows and doors. All reputable ICF manufacturers will have developed details for roof and wall connections, window and door penetrations, exterior and interior finish attachment, and virtually every other conceivable application. These details are designed to be robust yet practical. Designers should pay particular attention in the specification of the external and internal finishes, the penetration of walls for utility connections, and the location and routing of services, especially electric cabling and sockets. Finishes are normally applied directly onto the surface of the insulation. Plasters and lightweight renders will adhere directly to the insulation. Timber, masonry, curtain walling, and other claddings are applied over the insulation with appropriate mechanical fixings into the binders depending on the weight. The points at which utilities connect to the building should be identified prior to the concrete pour. This will allow for conduits to be placed through the wall so that the utility can enter. Once the concrete is poured and cured, channels or grooves are cut directly into the formwork using an electric hot knife or router. Plumbing and electrical lines are then inserted into the grooves and covered by internal wall finish. In addition to the easy and fast-track construction, ICF systems also offer improved site safety. ICF systems require semi-skilled labour only, and not highly scarce skills such as bricklayers. Training is normally offered by all ICF suppliers on site, and this can be learned quickly. ICF systems are light to handle, so there is less chance of injury. Heavy plant and equipment that you would normally find on the average building site when using traditional building methods is not required with ICF. This is due to the lightweight forms and the speed of the modular build. The workplace is easy to keep tidy, thereby cutting down the possibility of trips and falls. Minimal on-site cutting is required. Where necessary, forms can be easily cut with common carpentry tools to create special angles and shapes. On-site risk management is undemanding. During construction, it is necessary to support the formwork system and check for alignment during the pour, adjusting if necessary. The use of a bracing and alignment system is critical for construction of ICF structures. These systems not only assist in achieving plumb and level walls, they also provide an elevated working surface during the stacking process. Prior to the pour, these systems provide an active support to the stacked ICF wall, and during the pour assist the ICFs in maintaining a stable wall until the concrete hardens. The ICF formwork should be stored flat and protected against direct sunlight. Any use of agents containing solvents must be avoided. Most ICF manufacturers provide the proper pour pattern to use with their products. It's common to pour in 3 to 4 foot lifts, moving around the structure in a regular pattern until the top of the wall is reached. One of the reasons ICF walls are poured in lifts is because the concrete will begin to set or slake. This initial set provides strength and relieves some of the pressure on the blocks and eliminates the chance of a blowout. Once the formwork is in place and braced and the required reinforcement installed, concrete is pumped into the cavity. Forms need to be filled at an appropriate rate, based on manufacturer's recommendation, to prevent misalignment and blowouts. Ensure the pump has enough reach. A reduced diameter hose, such as 100 mm, should be adopted. 1. Foundations. Standard assessments of ground conditions and bearing capacity need to be made as usual. Accuracy in foundation is important with EPS insulated concrete formwork building system, which will ensure rapid construction of the walls. Levelling should be within plus or minus 5 mm. Rebar starter bars if specified by engineer. Foundations determined by structural engineer. Foundations should be set in conjunction with site datum point. Ideally, steps in footings should be at least 150 mm or 300 mm to coincide with half or full blocks. 2. Whilst setting out. Set up datum point at ground floor finish height. Set up string lines for perimeter of building. Square corners. Parallel lines. Check diagonals. Check wall lengths. Only after final check, load the site with formwork and tools. Have a waste disposal plan. Have the tools ready for the day ahead. Start at a corner. Work towards the middle. Never cut a corner block. Cut formwork at 50 mm cut lines. Never cut a web. If necessary to cut off the cut line, choose a door opening if possible. A cut off the cut line is a stack cut, which will need additional timber reinforcement internally and externally. Build 2 full courses. Do not remove any openings. Fit horizontal rebar on top of first course. Leave gaps in rebar for openings. With 2 courses in place, check for line, squareness, then level. Adjust as necessary. Mark the position of any openings on the formwork. Add a second layer of rebar if required, and be prepared to add any vertical rebar. Consider the addition of a DPC. 3. Rebar. Building control will require calculations from a structural engineer. The quantity, specification and location is determined by the structural engineer. Lintels will also be defined by the engineer. Prepare any links beforehand. 4. Third course upwards. Fit the second layer of rebar if required. Allow for any openings. Add the third and fourth courses of formwork, but leave out any formwork to form openings. Make sure all binders line up vertically. Check the height of any window sills and mark the position of any windows on the fourth course. Fit bracing within 300 mm at either side of each opening. Fix to the wall and the ground and set the wall plumb. 5. Openings. Calculate opening sizes for cavity closure. Build up walls to lintel level. Consider any additional insulation and/or screed above the slab when setting lintel heights. Fit the head closure first, then both vertical closures to support the head closure. Cut but do not fit the sill closure. This will not be fitted until the void beneath the sill has been filled. Additional temporary timber supports will be required vertically and horizontally. 6. Lintel design. Always consult a structural engineer. All openings must be fully supported with timber struts and wedges, both vertically and horizontally. 7. Checklist before concrete pour. Corners. Infill. Stack joints, replacement and strapping. T-connections, internal support and external. Penetrations. Some require sleeves, for example, water, electric, gas, heating oil and air exchange pipes. Those that don't, sewer, 150 mm heat recovery. For this type, make sure there is sufficient length either side of the formwork to cater for coupling. DPC blocks. Fitting radon barriers. Openings and closures. Lintels, links, cages, steel beams and timber strut supports. Intermediate floors. Wall plates. Bracing. Hot wire cutting. Slump testing. 8. Concrete design. Recheck the quantity required. C25 to C30 strength. Aggregate should be 10 mm for 100 mm and 150 mm core walls. 20 mm for 150 mm with minimal rebar and 200 mm core walls. Slump 150 mm to 200 mm max. Discuss rejection of load if the slump is too high. Will the pump reach? Frequency of trucks. 9. Concrete placement and consolidation. Pumps are the best. Ensure the pump has enough reach. 150 mm diameter hose must be reduced to 100 mm. Reduce the flow further with a swan neck, 2 90-degree bends. Thin wall flexible hose gives better control. Placement should not exceed 1.2 meter height per hour, so layer the pour with 1.2 meter high laps around the building. Slump test each load. To prevent voids and honeycombing, the concrete needs to be vibrated. Avoid external vibration. Use a maximum diameter poker of 30 mm with a long tail. Battery-operated pokers are easier. Work the poker directly behind the pump nozzle. Quick in, but slow out. 10. Floor connections. The diagrams shown here demonstrate how ICF joins with the floor structure. 11. Roof connections. Tips. Pre-cut the timber wall plate 100 mm by 50 mm. Drill along the length of the wall plate. Use a staggered format. Once the concrete has been levelled, bed the wall plate onto the wet concrete. Embed fixings through the wall plate into the concrete. Level the wall plate. Alternatively, embed fixings into the wet concrete and use to fix the wall plate once the concrete has set. If either opportunity is missed, drill and epoxy fixings into place once the concrete has set, at least 7 days later. The process is the same regardless of the roof structure: trussed, SIPs, steel or cut. Gable ends. Cut the forms to the designated angle, or wait until the roof structure has been fitted so that the gables can be built to the roof line quickly, easily and accurately. Placing the concrete requires a reduced slump. Use the poker with caution. Fix the designated anchors into the wet concrete. Trowel the top concrete flat to the line of the roof and protect from rain runoff and frost. Check the walls are plumb. Adjust if necessary. Radius walls. ICF allows curves, arches, intricate patterns and varying angles to be built. Special items can be made to measure and pre-cut in a factory, ready to be assembled on site. 14. Brick ledges and taper strip. 15. Waterproofing. For a straightforward DPC additive, just add a pore blocker type additive to the concrete when filling the walls, at or just above external floor level. Tanking is a specialist job and must be done by approved installers, well versed to the techniques involved when building with ICF. Basements must comply with BS 8102 standards. 2 layers of protection are required to reach BS 8102. Any combination between A, B and C depending on the risk assessment. Type A is external, a barrier, either sprayed, painted or draped onto the outside face of the retaining wall. Type B is structurally integral, mixed into the concrete as an additive during the batching process, with a water stop placed in the joint between the wall and the slab. Type C is a drained cavity membrane, fitted internally. Failure to comply with BS 8102 will be detrimental when applying for a mortgage. Rectification will be extremely expensive. Do not be tempted to dabble. 16. Render finishes. The diagram shows exterior render and wood finishes. The table shows recommendations based on maximum design wind load for attachments of batten with screws. 17. Internal services. The following should be considered. Electrical installation must always be done by a qualified electrician. Either always use conduit or non-migratory TPS cable, thermoplastic sheathing. Use a hot wire cutter to put chases into the wall quickly, cleanly and very professionally. Always put ducts through the walls prior to concreting if cables have to pass through the wall. Plumbing. Use the same hot wire cutter for chases to embed pipes, and always put ducts prior to the pour to carry water pipes through the wall. Interior fixings. For heavy load items, embed a sheet of ply into the wall by stripping off the top 12 mm of polystyrene down to the binders. The ply can then be fixed directly to the binder underneath the plasterboard, out of sight. For example, handrails, kitchen wall units, grab rails, and radiators, etc. Plasterboards. Fix directly with 45 mm drywall screws. No need to cut the plasterboards to size to fit the binders. Skirting boards. Mark the floor before skimming the walls, so all binder positions are known. Fixing skirting boards is now much easier. Or fix a 13 mm strip of ply along the bottom of the wall before plasterboarding. So long as the ply is lower than the skirting, it will remain hidden. The tools required for these types of installations include specialist items, along with some general builder's tools. Specialist items include large and small format hot wire cutters, slump tester, long-tailed 25 mm concrete vibrators, 2 units required, bracing system, rebar bender and cutter. General builder's tools include pruning saw and cross-cut saw, rubber mallet, retractable knife, foam gun, battery-powered screwdriver, 50 mm minimum length wood screws, 5 m and 25 m tape, string lines, laser level, wheelbarrows, shovels and brushes, timber bracing and plywood sheets. It's fair to say that the process from planning to delivery of a complete EPS insulated concrete formwork system takes approximately 2 to 3 weeks upon approval. Once delivered, as the fabricated elements are numbered and installation layout is provided, on-site stock management and assembly is simple and easy. This new housing project in Devon produced an insulated slab with a U value of 0.15 and external walls with a U value of 0.15. The developer particularly valued the fact that the unique high-density EPS cavity closure had a sufficient density to allow doors and windows to be fixed directly to it, thereby eliminating any cold bridging. The use of EPS systems enabled the structure of this large house, including gables and a large detached double garage, to be completed within just a few weeks. The speed of the program was made possible by the integration of the building components and a reduction in the need for extra on-site labor, especially in comparison to timber frame. Here is an example of a residential home constructed using EPS ICF building systems to create beautiful, rounded curves with a brick and render exterior. Here is an example of a large bungalow of 182 square meters. This was built using EPS ICF building systems to achieve high energy saving standards. An 820 square meter daycare center was built with EPS ICF building systems to achieve higher energy saving standards. To summarize, we hope that this CPD has helped to enhance your understanding on the history and benefits of ICF buildings, ICF as low-energy building systems, and the key features, EPS as ICF building materials and the characteristics, the key steps of ICF construction process and considerations. We also offer CPD on the design and construction of low-energy buildings, XPS, insulated concrete raft foundation systems. Thank you for watching our CPD. For more information, visit www.jackon-insulation.co.uk.